So, good morning, students. Welcome in next lecture of Math F242. So, presently we are doing game theory. Last time we were doing this example. So, just quick recap of this example. Let's player A has three alternatives, and player B also has the three alternatives. A3, B1, respectively. Their payoff is given to you 1 minus 1 to 5 minus minus 2. So last time we have seen this is the problem of the mixed strategy, right? So for that we have computed the row min, and from that max min as a minus 1, column max, then we compute the min max as a 3. So here we have seen the value of the game lie between minus 1 to 3, right? Then after we compute audio video, okay?
The audio was
Audio video is
breaking.
okay.
The voice was breaking for a while.
Let's check again. So here we have, we compute the expected payoff corresponding to when is you choosing pure strategy as A1, A2, A3. So following are the expected payoff for the player B. Now audio is okay.
Yes, sir.
So corresponding to A's pure strategy, following are the B's expected payoff, and corresponding to B's pure strategy B1, B2, B3, following are the A's expected payoff. So when we have the corresponding to B's pure strategy, here we write the expected payoff, right? Or means horizontally we write the expected payoff, and here we write the right age expected payoff, or B's expected payoff corresponding to the age pure strategies. So from here, the value of the game we define either the min max of these three or max min of these three. So from here, if you want to write the player B game or player A game, so you can write player B game as minimization of the Z, minimization of V, right? And where V is what? It is the maximum of these three. So when maximum of these three means all are less than V, so we have written this. Similarly, for the player A game, we write the maximize of V, where V is minimum of all these. So when V is minimum of all these, so all are greater than V. And here all the Y's, J and Xi are probabilities. So it will give you y1 plus y2 plus y3 is equal to 1, x1 plus x2 plus x3 is equal to 1. V is the value of the game, can be positive, can be 0, can be negative. So V is the URS, uncertainty sign, and being a probability, y1, y2, y3 are non-negative, x1, x2, x3 are also non-negative. Then after we now this is the linear program. So we have to solve. So solution for the player A problem. So here when we writing the player A problem, this is the player A problem. So maximize Z is equal to, maximize Z is equal to. So you know that in the standard form always we write the slack means all the constant on one side and all the variable on one side. So if V is given to you as a URS, so V can be written as v1 minus v2, and to remove the inequality less than, we have to add the slack variable. So here we are adding the slack variable s6, s7, s8, right? And we are replacing the v by the v1 minus v2. And in the fourth constraint, we have to add the artificial variable, then only you can solve. So here the v is equal to what? V1 minus v2, where v1 and v2 both are non-negative. So in this case, the x1, x2, x3, v1, v2, s6, s7, s8, and r9 are also non-negative. So now this is the standard form. So here, by the two-phase method, in the two-phase method, first we have to solve the phase one. In the phase one, we consider the objective function minimization of r, the sum of the artificial variable. So here we have the phase one. So from the optimal table of the phase one, or in the optimal table of the phase one, we replace the objective function of the for the phase two. So here we will get the optimum solution. So from here we can see, this is the value of x1, and this is the value of the x2, and here we write the value of the y1 and y2, and here we have the y3. So in this, you are getting the x1 as a 2 by 3, right? X1 as a 2 by 3 and x2 as a 1 by 3. So x3 will be the 0, and value of the game here, it is given to you as a 1. So this will give you the value of the game, value of game. And from the theory of the duality, we can write, because you know the player B game is dual of the player A game. So y1 is equal to 0, y2 is equal to 0.5, and y3 is also 0.5, and value of the game is 1. Now if you have to solve the second problem, so what was the second problem? Means this we have solved by the player A problem, right? If you want to solve the player B problem, minimization of the z is equal to v, y1 minus y2 plus y3 y3 less than equal to v, 3 y1 plus 5 y2 minus 3 y3 less than equal to v, and 6 y1 plus 2 y2 minus 2 y3 less than equal to v, y1 plus y2 plus y3 is equal to 1, v is urs, and y1 y2 y3 are non-negative. So if you want to solve this, so first we have to write in the standard form. So minimization z is equal to v, y1 minus y2 plus 3y3 less than equal to v can be written as v minus y1 plus y2 minus 3y3 greater than equal to 0. Means you have to write all the variable on one side and all the constant on other side. Then v minus 3y1 minus 5y2 plus 3y3 greater than equal to 0, v minus 6y1 minus 2y2 plus 2y3 greater than equal to 0, and y1 plus y2 plus y3 is equal to 1, and v is urs, and y1 y2 y3 greater than equal to 0. So in this case, first we have to replace the v by the v1 minus v2, where where v1 and v2 are non-negative. Now when we have this, so to solve this, what we have to do, here we have to add the surplus variable. So let the surplus variable r s1 minus s1, let the surplus variable r is the minus s2. Here the let the surplus variable is minus s3. Because of the greater than, for the initial basic feasible solution, we require the artificial variable r1, r2, r3, and in this also you require one artificial variable r4. So now you can say, from v1 v2 greater than equal to 0, y1 y2 y3 greater than equal to 0, s1 s2 s1 s2 s3 greater than equal to 0, and r1 r2 r3 r4 greater than equal to 0. It means we have the table, we have the table for uh, v1, v2, x1, x2, not x1, x2, y1, y2, y1, y2, y3, then s1, s2, s3, then r1, r2, r3, r4, and on the right hand side we have the solution. Here we have the basic variable. So you can see, means either you apply the big M method, right? Either you will apply the M method, or you apply the two phase method, right? Because here we have the artificial variable, so these two only methods can be applicable. So here the problem is little tedious, means little big. So to avoid that, we can write the given problem in a simpler form. So for the simpler form, what we will do, you means when we are solving the value of the game, means when we are computing the value of the game, you have seen we can have either the negative, positive, or zero value, and its value will not affected when you add any constant. So if you add, now please listen carefully. When you add any constant in the payoff, there is no change in the optimal solution. When you add when you add or subtract any constant in the payoff matrix, there is no change in the optimal solution. So here we are adding here the c is equal to 4. Means in every payoff means entries, in the every payoff entries, here we have the payoff matrix. Here we have the payoff matrix. So here we have seen, means lowest payoff is the -3. So we want all the payoff entries positive. So for that we are adding a constant 4. C is equal to 4, so that each entry will become positive. Means first 1 plus 4, minus 1 plus 4, 3 plus 4, 3 plus 4, 5 plus 4, minus 3 plus 4, 6 plus 4, 2 plus 4, minus 2 plus 4. So what is the benefit? The benefit is that here when we add, so benefit is that all the entry will become positive, right? All the entry will become positive. And if you compute the rho mean, there is no effect, right? Rho mean will increase by 4 only. So rho mean is 3, rho mean is here 1, rho mean here is 2. When we compute the column max, so it will become the 10, it will become 9. Here we have the 7. So this is the min max and this is the max min. So you can say that value of the game lie between the 3 to 7, right? Value of the game lie between the 3 to 7. So it is again the mixed strategy problem. So mixed strategy problem. So for this, if you write, if you do the same procedure, right? Here you write the associated probability x1, x2, x3. Here you write the y1, y2, y3. So what will be the problem? Yes, what will be the expected payoff? Yes, you can write na expected payoff. So corresponding to this, expected payoff will become 5y1, or you can say 5y1 plus 3y2 plus 7y3. Here it will become 7y1 plus 9y2 plus y3, 10y1 plus 6y2 plus 2y3. And here the expected payoff will come 5x1 plus 7x2 plus 10x3 3x1 plus 9x2 plus 6x3 and 7x1 plus x2 plus 2x3, right? So here we have to do, so for this, because it is in the row, so for this first we have to first we have to compute the min, then we have to do the max. So it is the max min of these, and for this it is the column. So for this we have to compute the min of max. So when we are writing the min of max, so what is the b's problem? Actually, I have to write that first, then I have to write this. So what is the min max? So let's say v is equal to what? Min max of 5y1 plus 3y2 plus 7 by 3, 7y1 plus 9y2 plus y3, and 10y1 plus 6y2 plus 2y3. This will be the whatever the theory you know with this. So what is the problem? Minimization of v subject to now v is what? Maximum of this. So maximum of this means all are less than v. So it will become the 5y1 plus 3y2 plus 7 by 3 less than equal to v. Then it will become 7y1 plus 9y2 plus y3 less than equal to v, and 10y1 plus 6y2 plus 2y3 less than equal to v, and y1 plus y2 plus y3 is equal to 1, and v is now v is now not a urs, because now the value, please listen carefully here, now all the payoff are positive. So value of the game cannot be negative or zero. So here the value of the game now will be the positive, and y1 comma y2 comma y3 greater than equal to 0. So when we have the minimization of the v, now clear up to here, because now I'm going to change. Up to here, any doubt? So great, I think there is no doubt. So minimization of the v can also be written as maximization of 1 upon v. Either you compute minimization of v or maximization of v. Maximization of 1 upon v. There is no difference. Clear? Since v is non-negative, v is positive, non-negative, instead of saying non-negative, you can say it is a positive only, right? It is positive only. So when v is positive, there is no problem in writing 1 upon v. Due to this step only, we have added there c is equal to 4. We want apparently the positive value of the game, so that we can compute 1 upon v. If you take 1 upon v with the original problem, so if it is a fair game, it will give you 1 upon 0, and that will create the problem. So we want our value of the game as a positive, so that we have added the c is equal to 4 there. Now this one can also be written as, from here we know that y1 plus y2 plus y3 is equal to 1. So this one can be written as y1 plus y2 plus y3 upon v. So that's we have written here. So now let us assume, let y1 upon v is equal to y1 dash, y2 upon v is equal to y2 dash, and y3 upon v is equal to y3 dash. So our problem will become minimization or maximization of y1 dash, y2 dash, y1 dash plus y2 dash plus y3 dash. And when we take this v in the denominator, when we take this v in the denominator, it will become 5 upon 5 into y1 upon v, 3 into y2 upon v, 7 into y3 upon v, and y1 upon v, y2 upon v, and y3 upon v can be written as y1 dash, y2 dash, y3 dash. So our constraint will become 5 y1 dash plus 3 y2 dash plus 7 y3 dash less than equal to 1, 7 y1 dash plus 9 y2 dash plus y3 dash is less than equal to 1, 10 y1 dash plus 6 y2 dash plus 2 y3 dash less than equal to 1. And since y1 y2 y3 are greater than equal to 0 and v is positive, v is positive, so their ratio will also be non-negative. So this will implies y1 dash, y2 dash, y3 dash are also non-negative, and v is also non-negative. So when v is non-negative, so what is the advantage? Here just you have to add the slack variable s1. Here you, no, here you have to just add the slack variable s1. Here the s2, and here you have to add the slack variable s3. So advantage is that now you have to apply only the simple or basic simplex table. So here the variables are y1 dash, y2 dash, y3 dash, s1, s2, s3. There is no requirement of artificial variable. It means there is no requirement for applying the m method or the two phase method. So just we have solved, right? So this is the solution optimal table. So from here you can say that this is the value of y3 dash, this is the value of y2 dash. So from here, and this is the optimal value, means it is the value of 1 upon v, right? This is the 1 upon 5 is nothing, it is the value of 1 upon v. So now please see carefully. Now important thing is coming. So 1 upon v, here we have the 1 upon v is equal to 1 upon 5. This will implies v is equal to 5. So actually this v is the value of the game for the transformed or modified problem, right? In the payoff we have added the c is equal to 4. So for the actual problem the value of the game will become the 5 minus c. So 5 minus 4, it is the 1, exactly same whatever you got there in the original problem. And what is the y3? Y3 is the y3 dash in, you know what is the y3 dash? Y3 dash is the y3 upon v. So y3 will become the y3 dash into v, and y3 just now we have computed as a 1 by 10, right? 1 by 10, and y2 dash as a 1 by 10. So y3 dash will come 1 by 10 into 5, that will become the half, and y2 is equal to y2 dash into v. So 1 upon 10 into 5, that is the 1 by 2, and y1 is what? Y1 dash into v, that is the 0 into 5, that is the 0. So in the last example you have seen, we have the value of y1, y2, y3 as a 0, 1 by 1 by 2, 1 by 2, 1 by 2. Right, here we have the value of the y1, y2, y3 as a 0 0.5, 0.5. So here we have written, right? So same we are getting here, the value of the game is we are getting like this, and x1, x2, x3 are 2 by 3, 1 by 3, and 0. So here you can see, so x1 is what? X1 dash upon into v. So x1, here we have the x1, this is the x1 dash, this is the x1 dash, this is the x2 dash by the theory of duality, and this is the x3 dash by theory of duality. So here x1 is what? X1 dash into v. So 2 by 15 into 5, that will become the 2 by 3. x2 is what? X2 dash into v, 1 upon 15 into 5, that is the 1 upon 3, 1 upon 3, and x3 is the x3 dash into v, that is the 0 into 5, that is the 0. So you are getting the same result after the back modification. But main advantage is now we have the sorter table, and we have not to include the artificial variable. So it's up to you how you are solving. If you know the two-phase method, you can apply the previous method. If you want to apply the simplex method, only one method you want to remember, then you have to modify your basic payoff matrix. So any doubt? So that's all from my side in game theory. Anyone? Any doubt?